All right. So thank you very much, Luca and Ariel, for the invitation. And yeah, it's my great pleasure to be here to share with you some of this recent excitement related to the exam search, more specifically to enhance the exam photon conversion. This is going to be based on the recent work I did with Kim-Soo Son and postdoc at DASI and Su-Kong Yun, new faculty member at IBS. All right, so given that this is a Axiom workshop, let me not waste time to motivate why Axiom is interesting. All of us are very much interested in finding this beyond standard model particle. But let me just say a few words about the Axiom search in general, the global effort. In a very broad stroke, the Axiom search has a very well-defined benchmark, that is the coupling strength between axons and photons. And roughly speaking, the search effort can be divided into two categories. One is the lab search, the other is the astrophysical searches. And inside the lab, in each category, we can see that these search efforts can be further divided into a few subcategories. For example, inside the lab, there's accelerator or non-accelerator searches. And even for the non-accelerator search, we could assume that axion is dark matter. Then we get the radical abundance to help us. That is, some axions for free, in the sense that they are already there. We don't need to create them ourselves. All we need to do is to convert the axions to some photon signals, and then we can observe them. Or we could search for axions without assuming that they are dark matter. And that includes a few categories. That is also the main focus of the rest of the talk, which I'm going to say a lot more about. Beyond the lab, in astrophysical environments, we can also do similar things, either assume axions dark matter and look for their decaying signals, or without these assumptions, that includes a lot of recent effort, including the spectral distortion or stellar cooling, or they all fall into this category. So the axions, they do not have to be dark matter, but they can still change the astrophysical processes and leave traces in the astrophysical channels. And lastly, when the axion mass is a bit heavy, on the heavier end, the decaying rate is large enough so that they can even leave signals inside the accelerator, inside accelerator experiments, including beam dumps and also collider experiments. And at the opposite side, when the mass is very low, the Broglie wavelength is large enough so that they can even change the structure formation, and also they could leave traces in this galaxy kinematics. So just to emphasize a almost very obvious point, that is that the axions, because they can exist, their mass can be across many orders of magnitude. So depending on their mass and also, of course, the coupling strength, the phenomena they manifest can be very much different. So it's really a global effort that try to constrain the axion interaction strength with the standard model using many different ways, different approaches. So as I mentioned, the focus is going to be on the non-accelerator lab search, and without assuming axion to be dark matter. And this has a few categories, including the so-called light shining through wall experiment. So that is the thing that we are trying to enhance. So I'm going to delay this by 1 or 2 slides to say more about. That this category also contains other search efforts, including the birefringence, with many of you in the audience to be the expert. And this, roughly speaking, the birefringence experiment is just is to look for the change of a photon polarization due to the photon axion conversion. And more recently, there have been some very interesting ideas about how to further enhance the non-accelerator lab axion search without assuming axion to be dark matter, including the stimulated idea. But yeah, let's look at this light shining through wall search effort and why this is interesting. As we saw that the sorry, I think let me move this a little bit. So as we saw that inside the lab, if we do not assume axion dark matter abundance, we need to create these axions inside the lab. And that is a double-edged sword. Actually has advantages and also disadvantages. First, the advantages, the bright side is that since now everything happens inside the lab, we don't have to suffer from any astrophysical uncertainties. So personally, I have also worked on a lot of ideas using astrophysical channels to constrain the axion photon conversion. But here, since we are converting photons to axions inside the lab, we do not have to worry about the modeling of the axion flux, for example, or any astrophysical background. And just to quickly mention, that we know for a lot of axion searches, it contains 3 components, just like a lot of other searches relying on the oscillation phenomena. So we need to have the flux, which is the axion flux, and then we have the propagation. That's where most of the conversion from axions to photon happen. And we have the final detection. So we try to detect the photon signals after some distance, propagation distance. And since all these 3 components happen inside the lab, the background is low, and also the systematic uncertainties can be well modeled, well. This hints for very high confidence level discovery or rejection possibility for the axion theories. And because of the same thing, actually it also poses some extra challenges. Since we need to create axions inside the lab, and every time the axions convert to photons or vice versa, we need to pay the penalty of the coupling squared. And the coupling is the thing that we're trying to push down as much as possible. So this is a dimension 5 operator, so this is a dimensional coupling, but still this corresponds to a tiny interaction strength. And every time we pay a price of coupling squared, we lose some sensitivity. And in a way that this is also partly because this is also partly the reason that this part, the non-accelerator lab search without assuming axion to be dark matter, is so far the reach is still kind of above other astrophysical channels. Okay. So that is the challenge we need to pay if we want to achieve a high confidence level discovery capability or rejection capability. And to combat this limit, people have been using this high power laser beam so that the flux can be enhanced even though that conversion rate is low because of this twice conversion, as I mentioned. And another challenge is the limitation of propagation distance. So by that, I'm comparing that to the astrophysical distances. For example, in astrophysical distances, let's say, suppose that if axion photons, they converge to each other inside the Milky Way magnetic field, that could be kiloparsec or even longer distance. And for the cosmic distance level, that could even be longer, like even close to megaparsec or gigaparsec propagation distance. But inside the lab, all we have is, like at most, for a reasonable size experiment of this type, we could reach order 100 meter. So that is quite a short propagation distance. In order to combat that, people have been using very strong magnets so that the propagation distance can be somehow compensated by the strong field value, strong field strength. And there's a third challenge, that is the high axion mass, the sensitivity suppression. And that roughly corresponds to these slopes. So if you look at a lot of experiments, there's a very sharp slope when axion mass goes up. And that is actually due to a high power suppression. And in light shining through wall experiments, this suppression could be the axion mass to the 4th. So in the past, people have tried to try different ways to combat this limitation to extend the search sensitivity to higher XMS, such as by inducing some plasma frequency and to induce a resonance between the photons and axions. So in our recent work, we found a different resonance that could greatly enhance the sensitivity in this region when the axion mass goes up. And okay, so let's look at quickly this light shining through wall setup. So here's a cartoon, and that is to show that the general setup of the light shining through wall experiment. So for the light shining through wall experiment to work, we need to start with a high power laser beam, and we shine the laser beam across some magnetic field, and the photons will traverse the magnetic field. And as we all know, that photons could convert to axions inside the magnetic background. So a tiny fraction of these photons will convert to axions. And now we put up a photon absorber that is opaque to photons. And this is what people call the wall. And the wall will absorb the photons, and they will block the photons, but the axions, since they interact with the standard model particles so weakly, they don't even see the wall. So the axions simply pass through the wall. Now, behind the wall, we need to detect and confirm that this process has happened. So we want to detect the axions. The way we detect the axions is to put up another magnetic field. And a tiny fraction of the axions will convert back to photons because they oscillate to each other. And now, behind the wall, we put down a photon detector. So usually it could be different types, like the transition edge detectors, and put here to observe the photon signal. So this final photon would be the signal. Okay. And have these photons not converted to axions, there will not be any photon signals here because all the photons will be blocked by the wall. And because of the existence of axions, people could see tiny fraction of photons even behind the wall after the wall block all of them. So that is the idea of light shining through the wall. And here is a quick list of the ALPS-2 specifications. So for ALPS-2 is a next generation of anti-light particle searches. It's an experiment that has just started data taking in this year in May, and it's happening in DESY. And on the left-hand side, you can see that the green region is the combined non-accelerator lab search of the axions without assuming axion to be dark matter. And this includes a lot of different types of experiments, including the Biot fringes, the P-velocity results, and also ALPS-1 and also OSCAR, that different types of light shining through wall experiments. And now with the ALPS-2 projection specification, the new projection looks like this. Okay, so this is a zoom-in plot compared to the previous one, and the gray region here that corresponds to CAST and also the global cluster, I believe. And the message is that finally, the light shining through wall experiment can reach a high, like deep enough, so it's comparable or even stronger than other astrophysical bands at lower XMS. But at higher XMS, as we saw, because of this high power suppression, the conversion probability is suppressed by XMS to the -4, the power of 4 suppression. It still quickly loses sensitivity when we go to large XMS. Okay. And the so that is the thing that we're trying to improve. And also another observation is that all of these light shining through wall experiments, they are using constant magnet. So they are using the constant magnetic field that they all point to the same direction. And the question is that what if we change it to a different magnetic profile? So it turns out that these two questions, they can actually address each other, and let's see how they change the result. But the punchline is that we show if we use a non-trivial magnetic field, for example, a helical magnetic field, the experimental sensitivity can be greatly enhanced, and we could create a resonance to reach a lot deeper, even at high XMS. Okay, so let's see how it works. So just to quickly refresh the memory of something very basic, let's start with a constant magnetic field setup. And so that is the setup of all the large interval experiments so far we have looked into. And so how does it work? We set up a coordinate system, and we assume that the axion photon system is propagating in the z direction. And we assume that the magnetic field, so here this is the constant magnetic field, it points to the y direction. So because here we assume that the axion photon system is propagating in a vacuum, so the photons are transverse. So the field vector or the polarization vector can only point in the plane of x or y. So here I'm denoting that the photons do have a component of gamma x and also gamma y. Okay, and A is the axion. So here omega is the energy and ma is the axion mass. And of course, for this system, we can easily solve it numerically, but that doesn't tell us much about the dynamics. And to solve it analytically is easier if we go to the mass eigenbasis. By that, I mean we can do a rotation, change of basis, and in the new basis, this whole thing is diagonal. And that gives us 3 mass eigenbases. Each one has its own effective mass with a diagonal homotony. And from this, we can easily solve the whole thing, and each one just propagates with their own phase. Okay, as long as they don't, it's still a coherent system. And because here I assume that axion photon mixing to be a tiny number, so that for the first 2 mass eigenstate, they are mostly massless. The third one is mostly axion mass. Okay, and now here we solve the system, and we can check the conversion probability. So the way we do it is that we start with the axion state, we rotate that to the mass eigenbasis, and in the mass eigenbasis, each one propagates with their own phase. At the detection side, we rotate it back, and we check the overlap with one of the photon states. Okay, so that is the transition amplitude. We start with axions, we end up with a photon pointing in the y direction. And if we square it, we get the usual conversion probability. And here I'm not assuming any plasma mass because I assume this whole thing propagates inside vacuum. Okay, so far so good. That's just an old formula. And what if we change the magnetic field direction to another direction, but still it remains constant? The result shouldn't change, right? Because the physics shouldn't depend on how we set up the coordinate system. But still, let's write it down explicitly. This will come into handy just in one slide. So if we write down this system explicitly, we will have a magnetic field pointing in the theta direction. Theta is the angle between the magnetic field and the y direction. And so this one has both a component of in the x direction and y direction, and this is the new homotony. So this is the equation of motion in the relativistic expansion limit. Now we can either do the whole trick like before, or we could just rotate it back, right? That's easier. If we just rotate it back, we need a theta angle rotation to rotate this whole coordinate system by theta angle. And this theta angle needs to be chosen such that it's diagonalized. It gets rid of the 1,3 component. And so we restore the previous homotony. Everything is the same. We don't even need to repeat the exercise. So what we call this rotation is the V matrix, and that is a constant matrix. Now let's add a little bit of twist, pun intended. Now suppose that the magnetic field is pointing to a different direction at different locations. So here I'm starting with like a very simplistic scenario where the magnetic field rotates with a constant frequency. And what happens to it? We can still describe the whole system with the previous equation of motion, right? And at every point, we just write down the amount of component pointing in the y direction, pointing in the x direction. But note that here, this theta is a function of z. So if the theta angle or the orientation of the magnetic field now is a function of the propagation distance. And we can, of course, choose to restore the previous form, the previous homotony, so that we know that how to solve it easily by doing the same rotation. But note that here, this rotation, the theta, since the theta is a function of the propagation distance, the rotation matrix is also a function of the propagation distance. That means that at different locations, we need to rotate different amount of the angle in order to restore the magnetic field to be pointing in the y direction in my new basis. Okay, so what does it give us? If we, so now let's look at the equation motion. Let's do this rotation. We put in this rotation such that this whole matrix on the right-hand side, it doesn't have a 1-3 component, and each component after the rotation is a constant. On the left-hand side, because of the change basis, we will also have a bunch of V matrix. And note that now, because this rotation matrix is a function of the propagation distance, is no longer a constant, these two do not cancel each other. It's not like before. So we can rotate this and get rid of the 1-3 component, and each component is a constant with a little bit of extra. So this extra sort of reminds us of a gauge transformation, which indeed is the right intuition. But now let me not go into too far into that direction. So what we get is an extra piece that has something to do with the profile of the magnetic field. So remember that theta is the orientation of the magnetic field, and it's a function of z. Okay, and to write it out explicitly, we will end up with this extra piece in this new gamma gamma A, this new basis. And we can, of course, do a 45-degree rotation followed by a field redefinition to get rid of the I. And what we end up with is this. And this is interesting because we didn't start with any plasma frequency, any effective mass of the photon, but now we see that the diagonal terms, they are not 0, ma squared. Okay, and that means that we effectively induce some photon mass or some equivalence of photon mass such that we need to take into account this effect, and this affects how fast the photon system oscillate to each other. And let's compare with the previous axion to photon conversion probability. Without the photon mass inside the vacuum, the axion to photon conversion probability looks like this. This is what we derived just a few slides ago. Now, if we include this theta dot, which shows up as an effective photon mass or a combination of photon mass and the energy, we will have a new conversion probability. This conversion probability needs to take care of these diagonal terms, and they play the same role as the axion mass squared over energy. And here, this is the new derivation, and we see that there's the theta dot purely due to the profile of the external magnetic field. And we can also understand the previous suppression. So here, without this rotation, without the photon plasma frequency, what we had was this expression. So this is the conversion amplitude. And when if we crank up the axion mass large enough, this will give us a large suppression, and that is the source of the ma to the -4 suppression, the high power suppression in the previous constant magnetic field setup. And now the punchline is that if we design a magnetic field such that it matches the momentum transfer between axion and photons, this could cancel, and this amplitude can be restored to get even much larger. So let me not to run over time too much. Let me just quickly give you the result. If I choose ALPS 2 specs, 108 meter, and also 1064 nanometer laser, etc. And if I choose a large enough axion mass, this is what we get. So this is the propagation. This is the propagation distance, horizontal, in the horizontal way, and the axion to photon conversion. And the conversion will be effective in the first 2-3 meters, and then it starts to oscillate. It's heavily suppressed. This is in the nonlinear regime. And if we choose the magnetic field that matches with the momentum transfer, we can get a blue curve. And this can be checked numerically by solving the system, the couple ODE, without doing any tricks or change of basis. And we get the dotted curves, and they verify this new formula, and they show that indeed this improvement in the conversion probability can be orders of magnitude large at this axion mass. So let me quickly say one word about the experimental relevance. So we start to look for the helical magnet, and we found that actually 20 years, this has been used for more than 2 decades. So at RHIC, the relativistic heavy ion collider, people actually designed and used this, what's called the RHIC snake. So it's a magnet, it's a superconductor magnet, that rotates 360 degrees every 2.4 meters. And this is used to control the polarization of the protons collision. And this is a paper in early 2000, and by that time, we have already verified that after several years of operation, the failure rate is very low, and they have many of these such magnets. So what we end up with is that now if we use a constant magnet, this is the ALPS2 projection. And for a magnet with a period of about 2 meters, 2.4 meters, what we get is this. So here, this orange curve is to say that we are not increasing the baseline length, we are not increasing the magnetic strength. All we did is to add a twist in the magnet to use this type of magnet, and this is the resonance we can achieve. So it's almost all 2 orders magnitude enhancement. And for the maximal reach, if we manage to invoke a resonance at different locations, that means that we use different thetas to cancel different ma square over 2 omega, axial mass square over energy. What we get is that we will restore the whole system into the linear regime. It will no longer have any dependence on the axial mass. And that means that if we invoke a resonance here, the reach will be as deep as this. And if we invoke a resonance here, it's like this, and another resonance here. So the orange curve here is the combined floor of the resonance. That means that before we increase the strength of the magnet or increase the baseline length, simply adding twists to the magnetic field, this is how much we can improve. So this region is the amount of improvement purely due to a non-trivial profile of the magnetic field. And okay, let me maybe skip this and say, okay, so let me say this and then I'll conclude. So here we assume that the magnetic field matches with the magnetic field rotates with a constant, exactly constant frequency. So suppose that this frequency is not constant, which is what happens in the real world, and it changes values, and it fluctuates around the value with a certain frequency. So here I take the simplistic model where the frequency takes n values within this 108 meter propagation distance, and within each interval is a constant, and it fluctuates around the constant value that we try to aim for. So instead of having this improvement, we will end up with each one is one Gaussian realization of the magnetic frequency. And this is for one axial mass. We can repeat this for different axial masses and check how much sensitivity we lose if the field quality is not perfect. So if we put in a very large size of the noise, which is 10%, I'm going to show you why this is a large noise, with a low frequency noise, so it only changes 10 values within the 108 meters, we get this band. This is 95 confidence level, 95% confidence level. So if we do an experiment, the reach will be like 95% of the whole time will fall into this band. And if we have 1% noise amplitude, we will have this blue band. And for higher frequency, the effect is even smaller, okay? And all of these assumptions, even the 1% noise amplitude is very generous, because if we look at the ring snake magnet, what they do is that the magnet is about 5 Tesla and the period is about 2.4 meters. So this is 10 Tesla meter around that. And to check the field regularity, we can integrate the component over the period and at different locations. And if it's the rotation, the frequency rotates constantly, this integral will be 0. So the rig people, what they put to constrain this irregularity component is 0.05 Tesla meter. If you take the ratio, this is below 1%, okay, 0.5%. That's the component of the irregularity component of the magnetic field. So that's why I said like even 1%, that is very, so even for the blue band, 1% noise amplitude, that's already very generous assumption. Okay, so, okay, let me finish this And okay, let me skip the scanning part and conclude. Okay, so I want to say that the axion magnetic resonance is really a very generic phenomena, and it can potentially have applications in more than just light shining through the wall experiments. And more specifically, this involves what's called the Rabi oscillation of a two-level system. And this kind of oscillation has been found in many different systems already. And it's just that it's kind of new in the axion photon system. And so hopefully I managed to entertain you for about 30 minutes about this axion magnetic resonance idea and how the axion photon conversion can be greatly enhanced with a non-trivial magnetic field profile. And I showed you that with a helical profile, it enhances the conversion, but also with a harmonic profile, if we modulate the amplitude, it can also greatly enhance the conversion. And this is in space. If we change the whole magnetic profile in time, this can also work, meaning that if we have a magnetic field and it rotates in time, or it modulates with its amplitude modulates in time, this can also they can also induce such resonances. So okay, thank you very much.
Thanks, Dan. Okay. Questions? Please use the reaction button if you have any. Before we take other questions, I have a. So, have you thought of other applications like in astrophysics or in cosmology, because having a sort of strong and varying, spatially varying magnetic field is can be found, in many applications. So I wonder if you have thought of something else.
Yeah, we're working on a follow-up in a few directions. One of them is that, for example, inside neutron stars, we know that there's and also the pulsars, we know that if we take the simplest GG model, the magnetic field has a rotating component, right? And that rotating component can have like high regularity. The rotation frequency is quite constant, and also the frequency can be quite large. So that could potentially be one place to look into to see how much this actually enhances the conversion probability, because I don't think that was taken into account before. And also, like, another place that might be interesting is the TV photon transparency, and because for that, during the propagation, the magnetic field could also change orientations. But this effective rotation of the magnetic field, it could induce a enhancement, could induce this resonance, but potentially it's also there as an effective mass of the photons. So this can potentially even suppress the conversion if the actual mass is not the same as the rotation frequency. So that's also something that we are looking at, we are exploring.
Okay. Other questions?
So I have a question. So I got a little bit lost with the shape of the profile of the magnetic field.
Sorry. Yes.
Yeah, I got a little bit lost of the profile of the magnetic field. Can you please explain me that again?
Oh, the shape of the profile, I mean, is just that it's the magnetic field that has a constant magnitude, and it changes the orientation in a constant with a constant speed. So
it's like oscillating magnetic field, right?
No, it's a constant magnetic field. So, oscillating magnetic field, that's another story. It can also have relevance in the context of the axion magnetic resonance. But in this example, we put up a constant magnetic field, and changes orientations as a function of the location. Okay, and
this is called sometimes helical magnetic field, no?
Exactly, it's a helical magnetic field. So it's a helical profile, precisely.
So, but
of course, for a photon propagating along the Fourier axis is an oscillating magnetic field.
Right. So in a way that
that's the thing, because what mixes with the right, so the in this case the laser, the polarization which is parallel to the magnetic field, right, it's mixed. So is that the same effect as having a like oscillating magnetic field? I mean, oscillating in space, right? It's the same effect.
Oh, for the oscillating
because the component that mixes with the axion is the one parallel to the magnetic field.
Exactly.
Okay.
Right. Because you're absolutely right. So only the component that's parallel to the magnetic field will be mixing with it. So one way to understand this is just through the parametric resonance, right? So every time it gives this axion photon system a kick, and it kicks at the right moment, in a way.
Yeah. So the thing is that you need to, in the formula you show, you need to cancel, right, some parameter to have the enhancement, right?
That's right.
Right. So at which level you can produce this cancellation? Because if you have, I mean, for a perfect geometry of your setup, you can do it, but perfect is not real. So you will have some kind of, I don't know how to say, uncertainty in how you are setting up your. I mean, if it has some special oscillation, this frequency is not exact, right? It's
this, right? So I included some uncertainty in the frequency to show that if the cancellation is not perfect, and with like a certain amount of noise in the frequency, and what is the range? And as I showed that even if it is 1%, like the blue band, that is already a very generous assumption. In reality,
I see. And experimentally, how much you can get?
So experimentally, what we can get is this, right? If we use the Rig-Snake magnet, and this is like a sub-percentage component of the irregular component in the magnetic field. So this is below 1%. That means that if we use the Rig-Snake magnet, what we can achieve is that we can reach even better than the blue band. And Rig-Snake is 2.4 meters. So that is the resonance here, and it's almost to get to the best case scenario.
I see. Cool. Thanks.
Thank you for the question.
Okay, so there's a question from Andrea. Sure.
Hi, thank you. I heard that you were saying something about what happens when the photons acquire a mass inside the medium. Can you spend a few words about that?
Yes. Okay, I can quickly say a few words because I don't want to go over too much time. But if there's an effective mass of photons, what we get is that we get this formula. Okay, so here, forget about the theta dot. Assume this is 0, like a constant magnetic field. So what people have been trying to combat with a large axion mass region is to fit in some gas, some noble gas like helium, and to induce a non-trivial refractive index that corresponds to a plasma frequency, and that can be interpreted as the effective mass of the photons. So if the photon mass matches with the axion mass, you can also cancel this term. Okay, but this experimentally has its own limitations. It has its own experimental challenges. And what we do is that we induce a theta dot this term to cancel the axion mass. And this has nothing to do with the refractive index. It's purely due to the magnetic profile we pose, and it has a non-trivial profile. And in the end of the day, right, so these two terms is what people have tried. In the end of the day, we are talking to experimentalists now. It's possible to have like a 3-way cancellation. So we have the axion mass. We still induce some photon plasma frequency, But with a non-trivial magnetic profile, it's possible to have like a three-way cancellation, and that could potentially be something interesting to explore even experimentally in the near future.
Perfect. Thank you.
Mm-hmm. Thanks.